Hi, Fabien.
Yes. So so hello everybody. So I'm Fabien Cromieres, and so I'm going to present this work done with the GAST and Kyoto University. So I will dive right away into some kind of overview so that you can know right away if you're interested or not in this talk. So basically, a common and convenient way of expressing translation equivalences in machine translation can be with such formalism as synchronous context-free grammar, which like this will show state the equivalence between a Japanese sentence here, Japanese partial sentence here, and a part of an English sentence here with some non-terminals. So basically, what we are going to consider here is the possibility of replacing this right-hand target side with a lattice. So basically, this instead of this English string, we use this lattice, which can actually encode compactly many different such strings. So basically, each pass in this lattice can represent a string like this. And so the benefit we expect from this are first, better expressivity and convenience, and second, actually some better performances for the decoding in some cases. Well, I will explain that a bit. So that's for this overview. Now I'm going to state some specific motivation for this work. So basically, the original context of this is that we are developing a 3-to-3 translation system with actually on-the-fly translation rule construction. So I was discussing synchronous CFG before. Actually, that's not really what we are using, but so that was just because it's something people are familiar with usually. And in practice, it doesn't really make any difference. But in practice, just we construct the rules on the fly, and we don't really use SCFG. I'm sure most of you are kind of familiar with the paradigm of example-based machine translation. But just as a quick overview of our system, I'm using some slides of one of my colleagues here. So we have a set of, we have a large database of translation examples, which we pass into dependency trees. We do some alignment between the part of each example. And so when we want to translate a sentence, we are going to pass also this sentence as a dependency tree and try to find some matches in the database, some part that matches the input with the source side of the database. Then we can project the parts that match on the target side, and this way we have some partial tree that we can recombine to create the target tree, and therefore the translation. So that's all very simple. Now in practice we can look at how we are actually creating the partial trees, and more precisely, and more importantly, how we decide how to insert, how to combine the trees. Because, for example, here in this case, we have this part of the input sentence that is matched in this example here, which we can project on the target side here to obtain this partial target tree. Now, of course, this example does not cover the whole input sentence. We still have two nodes that have not been translated here. So in practice, one question is where are we going to insert the translation of these nodes into this partial tree? So there are basically several cases. The simplest case is when actually we have some we can find some word in the source side that is actually equivalent somehow to the input word for which we want to find the insertion point. So in that case, we have this Japanese word that means hydrogen that has the same relative position as plastic. So by projecting on the target side, we can guess that the correct insertion position for plastic would be here, like as the right child of the word is. Then, of course, there are situations where actually it's not as simple. So we can have here some nodes that do not have an equivalent in the example, because, okay, of course, these are different sentences. So in that case, one heuristic we can use is that we try to somehow respect the syntactic structure, and so since across languages, and so since this word is actually a child of this word meaning produce, we are going to state that its translation should be also inserted as a child of the word produced on the target side. But you see that already with just this rule, we have, in this case, basically 3 possible insertion positions. That's shown by these 3 non-terminals. So already we have some kind of ambiguity in the rule in the translation candidates we are generating. Additionally, we have the case of non-aligned word here that we may or may not want to add to the target translation, because okay, since they are not aligned, we are not really sure if they participate in the translation of the input sentence. So here, this is the word row. Very frequently, this type of thing happen also with article like the or which will be often not aligned, and finding out if they are necessary to the translation is not possible until we are doing the actual combination of trees. Something a bit different, but somehow related to our problem, is that basically, because of we might want to consider different morphological variation of some words depending on the non-terminals. Because, for example, here, depending on what we insert here, if it could be plastic is produced or plastics are produced. So there is also maybe some variation we want to consider here. So basically, at the beginning of this work, there was this idea that we wanted to be able to consider as much as possible many different combinations. And so, as you see, for this simple tree, which could be somehow expressed as a string that way, we would have actually the first thing we were considering was to actually just enumerate all possible translation, which in this case will mean that we would have 6 right-hand side, depending on how we choose the position of y and whether or not we insert the word row. But in practice, this is a simple case, but in practice we could easily have much more non-terminals and much more optional words, so which would lead to enumerating real large number of actually right-hand side, like maybe hundreds of thousands. So this is where this formalism of lattice right-hand side come to be quite convenient, because now we can actually express a very large, pretty large number of combination in a format that is compact, and also that is quite easy to integrate into a decoder for the translation. So, and actually now I'm going to talk about the issue of decoding with this type of lattice. So I suppose also most people here know what I'm talking about when I talk about decoding. So, well, basically the translation will be done in 2 steps. The first step consisting in building a set of right-hand side lattice for each part of the input. And the second step is decoding. That is, we try to find the best lattices and the best path through each lattice that will create the best translation. It's actually quite easy to adapt existing algorithms for this case. This could be seen as just adapting classic lattice decoding algorithms to the case with non-terminal, or just adapting putting algorithms to a case with lattice. So taking the first view, so I'm not going to get into many details about the decoding, but just to give a general idea of what we do. So suppose this would be some grammar describing the possible translations of a given input sentence. If actually the optimal translation is given by a model score obtained by just summing the value over each edge, so which means that we only have local scores. So this is a simple case. Then basically, if we just have one lattice, then just a vita-B algorithm will find the optimal path very efficiently. So that's something very simple. And so we can apply that for the vita-B for the lower level lattice. And for the higher level lattice, like this one, which contains non-terminal, we can just replace the score of the edge containing the non-terminal with the score of the best path in the lattice corresponding to this edge. And so this is just a straightforward adaptation here. So of course, in practice, we want to use an n-gram language model, which makes things a bit more complicated. But again, there is a classic approach here that is more or less consists in just keeping track of language model states that keep track of the information about which edge we have crossed previously. So now, for each lattice, at the end, we don't have just the one best score through the path of the lattice, but a best score for each possible language model state. But then after that, it's kind of behaves the same. So, and of course, because we have, in practice, the number of language model states will be too large, so we have to prune. So that's where we can start applying classic techniques like Q-pruning and also minimization of language model states. So actually, decoding is not really complicated. We are just leveraging a lot of algorithms that have been developed before for similar cases. So now what's interesting is that the complexity is going to be, of the decoding is going to be proportional to the size of each lattice. But each lattice can encode potentially a very large number of right-hand side rule. So now an interesting question is, given that the same set of right-hand side rule can be encoded by different lattices, the question is it interesting to try to find some lattice representation that will exhibit better behavior during the decoding? It is especially interesting to consider that question in our setting of example-based machine translation, because in practice, a given part of the input sentence will often match many examples that are slightly different but still quite similar. And as we are going to see, the lattice paradigm allows us to basically factor this similarity to make the decoding part easier. So for example, let's consider here this set of right-hand side that are extracted from different examples, but translate the same part of the input sentence. So the first thing we can say is that we can just merge all of them into just one lattice by just merging the start position and end position of each lattice. Then basically we can try to minimize this lattice into a lattice having less edges and less vertices, which basically so basically this lattice contains express the same right hand side as this one. There is one path in this lattice for each path in this lattice, but this one is smaller. And to go from this lattice to this lattice, it's again quite easy by just leveraging existing algorithms that were developed for FSA minimization. So again, I'm not going to get into the detail here. There are more details in the paper if you're interested. Okay, so basically we can somehow minimize the lattice representation. So now the interesting question is, does it bring some benefits in terms of decoding? So that's what we are going to see just right now. So basically we did some small experiments on some Japanese English corpus, which comes from the NTC IR10 patent empty task. So it's so this task was providing with pretty large training data, and we have been testing on a bit less than 2,000 input sentences. So these are very technical sentences, pretty large usually. So first I will consider the impact of the minimization I was just describing. So the first thing we can say is that the minimization does minimize the number of vertex and vertices and edges, because as we can see, applying our simple minimization algorithm basically divide by 2 the total number of vertices in the representation we have, and slightly decrease the number of edges. In terms of performances, this translates into actually a very large decrease in memory used when we are using this minimized representation, and as well as decoding time divided by 2. Okay, actually I'm not taking into account here the time taken by the minimization itself, because otherwise this would basically reduce the improvement by 2. But since in many cases it's actually interesting, for example, for tuning, it's actually interesting to translate several times the same set of sentences. I think it makes sense to just consider the difference in decoding time. Another experiment we did was to compare this approach with just using an enumeration of the possible right-hand side rules. Was that actually we used a state-of-the-art decoder, which is an open source decoder developed by Ken Heafield, and we expanded the lattices we had into basically flat strings, and we fed that to this decoder. And here we can see that again, by keeping a compact representation as lattice, our decoder can actually use much less memory than the one than the decoder developed by Ken Heafield. Apart from that, the decoding time was quite similar. Decoding time was quite similar, which so in practice, I believe, yeah, using lattice should have been faster than that, but I believe my implementation is not as optimized as the one of Ken Heafield, so the two things kind of cancel out. Search performances were basically similar. So I'm out of time, so I'm going to jump to conclusion. So basically, to just recap, what we are proposing is to use lattices to express right-hand side part of translation rules in a way that is both more convenient and allow to represent more compactly and more efficiently many translation options. We have shown that the representation of the rules had a direct impact on the decoding performances, which is something I think has not been tried so often before. So in the future, we plan to first optimize the code a bit more and also consider probably a bit better such strategies. The code of the decoder is actually available as part of the full Kyoto EBMT system, which is open sourced at this address. I have to say that currently the decoder is kind of just inside the code, so it's not conveniently to use right now, and there is not so much documentation. But I plan to make it standalone with some at least decent documentation in case somebody is interested in trying it. So yeah, that should be done in the very near future anyway. So that's all.
Okay, thank you very much for nice talk. And any question, comments?
Hi.
Hi.
Thanks for an interesting talk. I have two clarification questions. First, your baseline is a flat representation of rules. That your flat lattice, what does it look like? Is it just, are there no edges shared between rules?
You're talking, okay, so just to be clear, you're talking about this slide?
No, before you compact your lattice.
Before I compact my lattice. Talking about this slide.
Right. So is there, no, or I'll start differently. The decoders I'm familiar with use a tri-data structure, which you could also imagine as having some kind of compacted form compared to a flat representation of right-hand sides. So you think there is some kind of similar stuff going on between your compacting of the lattices and the converting them into a tri-structure?
Yeah, sorry, I couldn't quite hear. So you mean between my representation and which one? I couldn't really hear what you were describing.
Take CYK plus the Moses decoder that implements.
The Moses decoder, for example. So what happened in the Moses decoder is a bit different. So the thing, one thing is that this is done outside of the decoder. It's kind of a pre-processing somehow. So and this is so basically this will be more equivalent to actually converting the phrase table of Moses into a set of lattice, into this kind of lattice. So it's and actually this is something that could be done that just applying this for phrase-based translation by just minimizing the phrase table into this kind of representation.
All right, maybe the second question, if I may. If you use Canis search, what decoding algorithm do you use there in your baseline for the last slide?
For the last slide, what kind of?
You have the key search thing.
Which one? This one?
Yeah, Can-He-Fields decoder.
So what kind of baseline?
What kind of decoder do you parsing algorithm does the decoder use there?
What kind of parsing algorithm?
Is it CYK plus?
Like
yeah, it's a search, but it doesn't actually do the decode. Didn't change the parsing.
No.
Yeah, but
so
I think it's using CYK plus, and then it does the pruning. So the memory consumption there could come from the parsing algorithm. The difference could come from the parsing algorithm and not from the representation of the grammar?
No, this is just measuring the decoding. I mean, the parsing is done beforehand. So when I'm measuring this, I'm taking out the part that come before actually. So this experiment is just done from the point when we have already parsed the input sentence, matched the example, constructed the lattices, and then then this is when we start this actually.
Okay, thank you.
Hi, thanks for the talk, very interesting. Have I missed, you haven't reported anything as towards quality, even a blow score or something like that?
Yeah.
Or maybe I missed there?
Yeah, I guess it's a bit strange not to show a blow score on a machine translations track. There is some in the paper, I was going to put it, but then, well, how to say? In practice, I'm not sure what the blow score would show here because this is more about decoder and convenience of representation. But basically, I can tell you the system we are developing as, let's say decent blow score, usually at least as good as Moses in the...
I'm not so curious about the absolute value, but the comparison with the baseline, because you are filling the beams with a lot of options coming from the lattices. And even though, the coding time, memory, and complexity is all the same because they're constrained by, well, they're not all the same, but the performance in the end is the same because it's constrained by the beam parameter. So the width of the beam is what is going to give you the constraints on the time complexity in the end. You could be hurting quality a lot. Even though you're reporting model score, you could be hurting quality in the end. So it would be interesting to have a look at it.
Maybe yeah, I may be wrong, but it's okay.
We can take it outside.
Actually, I think you are familiar with synchronous binarization. Do you know that?
Synchronous
binarization, which is proposed by Hao Zhang, 2006 or something. Because in that case,
for hierarchical.
No, I mean that the binarization, but it's kind of making compact using lattice structure. And synchronous binarization implies that I think the grammar is kind of you have lots of non-terminals in the right hand side, right? Is that correct? In that case, that we can make it faster by binarizing on the fly, and that's the thing you can. It's my comment. So you try lattice side, and before we had a binarization using tree structure, and this is a kind of CFG. So CFG structure is much fit to this framework. This is my comments.
Okay, thank you.
Okay, and yeah, thank you very much. Thank our speaker again.
Thank you.